All right. So our next speaker is Minmin Chen from Google.
Thank you. Try to see if I can set this up. Nope. Okay. So I'm going to try to share our efforts in improving YouTube video recommendations from a reinforcement learning perspective. So this is actually a joint work with a lot of collaborators at Google. Ed, who's actually helped us start this exploration, is also in the audience, so be sure to talk to him and get his perspective as well. So I'm going to divide this talk into two parts. In the first part, I will try to motivate the work, talk about why do we want to use reinforcement learning for building recommender systems and the challenge of using them for recommender systems. And in the second part, I will try to share our initial success stories of using reinforcement learning for a YouTube video recommendation. And actually using these techniques leads to the largest single launch improvement we've seen in YouTube for the last 2 years. So hopefully I can motivate you to try out some of these techniques. So recommender systems are heavily relied in the industry to help users sort through a large corpus of content and find the very small fractions of contents they will be interested in. And no surprise, recommender systems are extensively used within Google to power different Google products. So they are used in YouTube to recommend videos, in Google Play Store to recommend apps, games, books, and music, and in Google News to try to personalize news stories for users, and in Google Maps to find restaurants for you to eat and hotels to stay. And in fact, there are many, many other use cases within Google. So in the last decade, we've seen the techniques that's powering these recommender systems evolved. So the first generation of recommender systems heavily relied on these user item interaction pairs. For example, in matrix factorization, we will learn kind of latent user and item embedding so that they will regress towards the few interaction pairs we have observed. And in the hope that by learning these representations, we can then generalize to missing user item interaction pairs. And with the kind of deep neural network gaining popularity in different fields, they also started to influence the recommender system community. So researchers try to use these techniques to build richer models of the users, as well as richer models of the items, for example, to address cold start issues. And these techniques are also relied on to kind of incorporate side informations beyond just the user item interaction pairs to improve recommendation systems. So we've seen these techniques bring almost like revolutionized advances to industrial recommender systems in early years, but these improvements are kind of saturated out lately. So the question we want to address is, how do we break out of the plateau? So the first and second generation of recommender systems are still fall within the supervised learning paradigm in our perspective. And there are several limitations with solving recommender systems as a using supervised learning approaches. So first, these systems and these algorithms basically take the feedbacks the user provided on the items as ground truths and try to build models to regress to these user feedbacks. But in reality, recommender systems are interactive systems where the recommender will be providing users with a few content, and the users will provide feedback on these contents. So as a result, we only observe feedbacks on items which the recommender the current system would have recommended, but not the others. So for example, in this case, we will see, we know whether or not the user likes these two videos, but then we'll have no idea if a different video is recommended, how much more or less the user would prefer that video. And ignoring this system bias could seriously impact the quality of recommendation we'll be able to give. And the second limitation is that these methods tend to provide myopic recommendations. So as in this example, because these methods are often optimized to maximize directly immediate response. So as a result, they tend to recommend content which are catchy or the users are more familiar with. So as in this example, so it will recommend a video which the user has already been familiar with. And as a result, users do not get additional information from these watches. And in the worst cases, it can even recommend videos which are kind of clickbaity or eye-catching, but then it can hurt the user's trust on the platform in the long run. But on the other hand, what we would like the recommender system to do is to actually planning for the long term, so that it will recommend videos that can actually broaden the user's interest group, so that they can lead to more longer-term user utility. So every, I guess, recommender system researchers will probably have their vision of what would they like the next generation of recommender system to be. So from our perspective, what we want the recommender system to do is kind of form a partnership with the user as they navigate the platform, so that the recommender system is not only able to kind of adapt to the user's interest quickly, but also help users discover new interests, so that we can optimize for long-term user utility. And we believe that reinforcement learning is actually a great tool for us to achieve that. So reinforcement learning are naturally designed to plan a sequence of actions so that they can actually change the underlying state and maximize long-term reward. And second, there's a large body of literature in reinforcement learning that deal with this kind of bandit feedback, where you only observe feedbacks on actions you have already on actions you chose, but not the others. So using techniques such as exploration and off-policy learning. But applying reinforcement learning in recommender systems is not straightforward. So there are a lot of challenges coming from the specific setups we have in recommender systems. So first, we usually deal with a much bigger action space than the regular standard applications for RL. So in our case, we have to sort through like millions or billions of videos in order to recommend. So the action space is in orders of millions or billions. And if you want to do set recommendation, then the action space is even bigger. And second, exploration is actually much expensive in the recommendation settings. So you can easily imagine if the recommender just show you random content, that could definitely lead to very bad user experience. And third, so actually most of the data we deal with is coming from off policy. So it's coming from a behavior agents which actually have a different policy than the ones we are learning. So we need to be able to do effective off-policy learning. And fourth is that, so in the recommender system cases, actually we do not observe the underlying state changes. So the user is not going to tell us explicitly what they are interested in, and we have to infer the user interest from the activities they have on the platform. And fifth, of course, we have very noisy and sparse reward signals coming from the users. So here, I'm going to try to share some of the work we did in this domain, trying to address some of the challenges we have. So I'm going to try to stay at a relatively high level, but if you want to know more details of this reinforced recommender, please come to our talk on Wednesday. So YouTube, as one of the largest video hosting platform, has been attracting like billions of users and creators. And so people do spend a lot of time on this platform. So it was reported in 2017 that the viewership in YouTube is actually surpassing the time people spend in TVs. And actually, the most of the increase in viewership was caused by using these personalization algorithms, in other words, the recommender systems. So the recommender system that's powering the YouTube video recommendation is a multi-stage recommender. So it selects, it goes from a video corpus of billions of videos and try to select a few dozens of videos for user to consume for each user request. So in this work, we focused on the candidate generation part, where its goal is to going from the video corpus of billions of videos and narrow it down to a few hundred most relevant to pass to the second stage. So there are a few challenges we have to address in building this recommender. So the recommender has to accommodate billions of users whose interests are constantly shifting as they interact with the system. And actually the platform hosts billions of videos which follows a long tail distribution, which means there are a lot of videos which are not receiving tons of views. But then they are still very relevant to a small group of users, and we want to be able to recommend them. And a combination of both means that we'll have a sparse and noisy user feedback. So how do we convert this candidate generator recommender into a reinforcement learning one? So in RL, we are trying to build agents which can take actions in some environments so as to maximize some notion of cumulative reward. In this case, the agent we are trying to build is this candidate generator. And the environment which is captured by the state transition, and a reward function. So the state here should basically capture the user's interest as well as the recommendation context. And the reward should capture a user's long-term engagement or satisfaction with the platform or the recommendations. And the action the agent can take is to nominate videos from a catalog of millions. So in the following slides, I'm going to try to walk you through on how we build the state representation, how we come up with a reward, and how we choose actions. So the data source we use to build this agent is the user trajectory. So for each user, before our recommendations, we have access to a sequence of user activities on the platform, which videos they watched, which one they liked, what's their search query looks like. And we call this part of the trajectory the sequential path. And after our recommendation, we also have access to the user's feedback. Do they like our recommendations? Which video they watched after? Which videos they like? What's their comment? And these we call the sequential future. And in the following, I'm going to discuss how we use the sequential path to come up with our belief of the user state. and how we use the sequential filter to come up with the reward. So in building up the state representation, as said, one of the challenges is the partial observability. So the user do not tell us about their interest groups or how happy they are with our recommendations. What we did is that we based on the user activity on the platform and try to figure out what's their interest. So what we did was we take the user watches that's right before our recommendation, we send them through a recurrent neural networks, and the RNN is going to aggregate these events and produce a dense vector, which is our representation of the user state. One thing that's worth noting is that actually the context of the recommendation matters a lot. So the context of historical events is going to influence how much they will change the underlying user state for each event. And the request context is also going to change our recommendation significantly. For example, we would probably want to recommend very different videos when the user are browsing on desktop or mobile phones. So we tested these ideas in multiple live experiments and observed very significant improvement on the main online matrix. Now let me talk about the reward part. So one of the so to address the issue of the supervised learning approach, where you only care about immediate response, here we want to aggregate the all the rewards that's coming after our recommendation, so that we can give actions which lead to longer-term engagement a boost versus just rewards the actions which focus more on the immediate returns. But to deal with the noise in the user feedbacks, we try to aggregate the future reward with exponential decay. So in our live experiments, we see that when we move from a myopic recommendation towards accounting for future reward, we saw a 0.3% again in online matrix, and this is kind of one of the larger improvements on YouTube. So in the last part, I'm going to talk about, so how do we, given this user state representation and the reward function, how do we choose actions? So there are many approaches in RLs to help the agent choose actions. In our work, we decided to go with the policy-based approach because it is actually directly try to maximize this quantity that we are interested, which is the long-term reward. And also because of its stability compared to a value-based approach. So in this reinforced recommender, we're trying to learn a stochastic policy pi theta, which is going to cast a distribution over our action space given a user state, so that we can maximize this cumulative long-term reward. So the trajectory tau here is the trajectory generated by following the policy, and the cumulative reward is the total sum of reward for the entire trajectory. So because we have an explicit form of the policy, then we can basically optimize the policy parameter thetas by doing gradient ascent on these parameters. And because of this log trick, so actually the gradient end up looking exactly like the gradient of weighted log likelihood, with weight proportional to the long-term reward. So in the sense that actually the learning part of reinforcement learning is actually very connected to supervised learning, where you would actually optimize for the likelihood of observing the next action. But what reinforcement learning offers us is a tool to think about exploration, think about planning, and think about changing actually the underlying user state. So a common choice of to parameterize the policy is to do a softmax over all of the actions. But in our case, because we have to deal with this large action space of millions, so in learning, we did a sample softmax to avoid this expensive computation of this normalization factors. And at serving time, we did a fast nearest neighborhood lookup before we actually sampling from a subset of the action space. So one of the actually biggest gain we gain from these lines of work is to do our policy learning to address the system bias. So in our case, also one of the distinct facts of building a recommender system versus the standard IO application is that we only have access to data which are of policy. In our case, we have an agent which is refreshed every 5 hours, which means the agent's policy after in 5 hours ago could be very different from the target policy we're trying to learn now. Meanwhile, we also have traffic which are acquired by other agents which have very different policy than the policy we are trying to learn. So as a result, we have to address the system bias which caused by having only access to log data which are generated by a different policy. So there's actually many works which are kind of similar to what we did here. So there's this counterfactual learning literature. It's also similar to what people have been doing in the domain adaptation cases, where basically what we're trying to do is to add an importance weight which tries to weight the trajectory based on how likely is the trajectory being generated by the target policy versus the behavior policy. So we did actually a whole body of work trying to control the bias and variance in this importance weight. So if you want to know more details, please come to our talk on Wednesday. So one of the, as we said, without addressing the system bias, we could just end up recommending an item, not because the item was relevant, but instead just because the previous system are more likely to recommend that item. So we've seen that in our live experiment, before we apply this off-policy correction versus after we apply, we can see that there are much more traffic that's coming from the tail recommendations versus before, which basically tries to follow the prior system and recommend more head videos than tail. So in the live experiment, so we also observed 0.86 overall matrix gain. So this is actually the largest single launch we've had in YouTube for 2 years. So to conclude, we've built our initial kind of attempt of trying reinforcement learning for recommender systems, and we had quite a bit of success with it. So hopefully you can also think about it and try it in your use case. But of course, there are a lot of future work we are trying to do in this area in terms of building a better state representation so that we can account for longer range dependencies in the user state. having better exploration strategies and planning so that we can really lead the users towards a different state versus they just recommending content that are familiar to the users. And so far, we have been constraining ourselves just thinking about the systems and users, but actually in YouTube, there's also the creators. So want to maybe have different utility functions to optimize so that we can improve the overall YouTube ecosystem instead of just focusing on improve the user utility overall. Yeah, with that, I can take questions.
Thank you. Questions?
So I have several questions. The first one, I think in your slides you kept showing this online metric. What is that online metric? Is it CPR, dwell time, or anything else?
I don't think we can reveal what's the, I mean, there are multiple metrics we are looking at in our live experiments. Some of them are more engagement driven, and some of them are actually measuring the user overall satisfaction with the platform through a kind of survey. Yeah, so this is one of the metrics we are looking at.
So right now, how do you address the co-start problem with this reinforcement?
You mean co-start on the item side?
On the user side.
On the user side. That's a good question. So right now we are mostly relying on this user pass activities to kind of learn this user state representations. So if a user does not have any past histories, then we kind of are in the lost. But then we are thinking of actually other ways to incorporate the user profile into the state representation building so that that can hopefully address partially their co-start issue.
Other questions?
So in terms of this application use case, here you only, I think it's adding a new candidate generation. So the decision, final decision could be affected by other candidate generation and final ranking. Have you considered optimizing all of this jointly by considering like more types of factors?
Yeah, that's a very interesting question. So it does touch upon on this kind of whole YouTube ecosystem. So right now, what we are trying to do is we do make utilize of the other candidate generators traffic. So by taking them into our learning, so that in the sense we can sort of learn from kind of mimicking their good behaviors. But then there are also work coming out from the team try to account for example, the interactions between the candidate generator and the ranker, how to better integrate the two processes so that it will lead to a better recommendation in the end.
So usually in the reinforcement learning frameworks, like in the initial stage, the agency is not smart enough to give you good recommendation. Then, like, how do you solve that problem?
It's a very interesting question. So indeed, we actually transitioned from an agent which is kind of doing purely mimicking from previous system. So in the sense, the agent is having a reasonable levels of performance. And by incorporating like this policy learning and long-term rewards is try to shift from this original behavior of just mimicking the prior system towards really optimizing for the long term.
So you talk about to change the optimization target from the short-term, from media later you show this CDF report will be indeed simple tracking from the tail path. So I wanted to know on the system level, will this change the behavior of user, say the user on the aggregate spend more time on YouTube, or there will be more traffic on YouTube system?
Yes, we actually do observe like this very interesting user learning process as well during our experiments. So there is this growing impact of our improvement during like even just 2-3 weeks period. We see like it's kind of a move from a neutral-ish improvement towards a bigger gain, where the user is actually also adapting to this new behavior exhibited by the system.
In the back?
So I want to ask, so we are the same improvement you get on the less active user compared to the active users?
It's a great question. So we haven't really been trying to tease out whether like the improvement is more coming from the heavy head users or the tail users. But usually the kind of tail users are also more interested in the tail content. So maybe the shift in kind of traffic towards the tail also suggests maybe we're dealing better with the tail users. Yes.
When running these A/B tests, how long did you measure the changes?
So we ran it for like usually several weeks, and then after that we also ran kind of holdback experiments, even much longer term holdback experience where we will hold back the system for months and try to see if the gain, I mean the difference between the control and the experiment group. Yes.
So when you run these experiments for months, how do you deal with the cookie share from how you're able to kind of, so like, are you tracking your users through cookies, through the browser? So with these long-term experiments, you have huge cookie share. How are you able to track them for that long?
So, I mean, if a cookie expired or get cleaned, I think they will be just dropped out from the long-term holdback.
Yeah, but that's also a kind of survivorship bias too, because some users might not come back because like they hated the treatment versus users who never showed up because they didn't get here. So it's going to be hard to.
Yeah, that's a good question. I don't have a good answer right now. Maybe I can address later.
Well, thank you again, Minmin.
Thank you.